Hey guys, welcome to another episode of Idle Instructions, and today we're going to be looking at Ohm's law and seeing why it's important to our circuit that we built in the last episode. So let's get straight into it. So Ohm's law just states that the voltage of a circuit is equal to the current multiplied by the resistance, and this is given by the formula V equals IR. In this case, V is the voltage, I is the current of the circuit, and R is the resistance. Voltage is measured in volts. The current is measured in this unit called amperes, and the resistance is measured in this funky unit called ohms. So that's the three different variables that are used in Ohm's law. So we can actually then rewrite these formulas to figure out the current and the resistance. So if we do some basic high school maths, we can rearrange to have the current equaling the voltage over the resistance, and we can get the resistance to be the voltage over the current. So these are the three ways you can find out all these different values, and that's Ohm's law. Now let's take a look at what these values actually are, and I'm going to use the analogy of gravity to sort of explain what voltage, current, and resistance are. So now if I take this Sharpie that I'm just about to grab and I drop it at this height, let's say that's 12 volts. Now if I vary the height of this, we sort of intuitively know that the force at which the Sharpie is going to hit the desk is going to be more or less depending on the height that I drop it from. So if I raise the Sharpie up, we can say that this is increasing the voltage. The amount of pressure or force that it's going to exert on the desk is going to be a lot more. The rate is then how many of these Sharpies are going to drop per second, say, through a given area. So if I have a really fast current, I'd be dropping it very fast, and there'd be a lot of them going through. And then the resistance is just whatever is pushing back. So air resistance, or if I had a hand in the way or something like that. So this sort of equates to those three principles in electricity as well. So I've drawn out the circuit that we made in our last video here on this book. Now, this represents all the different components that we used. So at the bottom here, we've got the Uno R3, and I've got the two entry and exit points, pin 12 here and ground here. Now, this is the resistor on the far left here. So we'll just label that. So this zigzaggy line is what represents a resistor. And I'll just write that in there. Then any straight line that you see in a circuit diagram is just whatever is conducting or transferring the electricity between the components. So here we've got the jumper cables that go between the Uno R3 and the breadboard, as well as all the metal contacts that are in the breadboard itself. Then up here, this funky looking arrow is the LED. So we've got 5 volts being used across the entire circuit, because that's the amount of voltage that pin 12 outputs. In a perfect world, it's a bit less than that, but we'll just use that for reference. The LED has a forward voltage of 2 volts. Now this is sort of specified by the manufacturer, and it says that this LED needs 2 volts to work. But we've got 5 volts. So what's going to happen is the current is going to be too excessive for this LED with our current circuit without the resistor. If we didn't have this resistor, the current would be enough to potentially blow up the LED or, just break it entirely. So what we can do is we need another component to use the rest of the voltage. So we've got 5 volts, the LED uses 2, we need something to use up the remaining 3. So this is what the resistor will be used for, to use up the remaining voltage and restrict the amount of current that goes through the LED. Now, current in a circuit or in one single loop like this stays continuous throughout the entire loop. So whatever passes through the resistor will also pass through the LED. So basically, the LED has very minimal resistance, so we can dictate the amount of current that passes throughout the entire circuit just by using the resistor. So we know that 3 volts is being passed through the resistor, and we also know the current that will be required for the LED. Now, I think for this LED, the manufacturer says that it's 20 milliamps, so it could be 30 milliamps, but it's okay to go under. It'll just mean the LED is dimmer. So if we actually use Ohm's law that we looked at earlier, we know that the voltage is equal to the current in amps times the resistance. So if we're using 3 volts for the resistor and we want to have 20 milliamps going through it, we actually have all the variables we need to figure out what the resistance is using that other formula. So here I've written 3 divided by 0.02 amps, because it's 20 milliamps, so you have to divide it by 1,000, is equal to the resistance, and that turns out to be 150 ohms. So if I put in a 150 ohm resistor in this circuit, it'll mean that 20 milliamps will flow through that and then eventually hit the LED, and we'll get a LED lit up. Now, the LED will be slightly dimmer than what it's capable of, depending on what the milliamp requirement is, or the maximum milliamp. So I think for a lot of these, it's actually 30 milliamps, but you'll have to check with your own LED specification sheet to see what that is. So I hope you enjoyed this video and found it very informative, and I look forward to seeing you in the next one. Goodbye for now.